Not like it.
Producer, are we live? Producer Ryan? We're good to go? Okay. Hello, everyone. Welcome to Saturday School. Number 3 is, all of you probably know, network-based games are becoming more and more popular. The technology behind it is getting more complex. And so we have with us a really fantastic speaker, Basudev Patel.
Hey, guys.
And he's a lead Unity engineer here at LILA. And I'll let you go ahead and explain what you're talking about. Take it away, Basudev.
All right. So this talk's titled Structure of Networked Action Games. So there's kind of these fundamentals of how we should think about games, and that's kind of what this talk is going to be about. But these fundamentals also help us write multiplayer games in a way where they look smooth, they are very responsive. Responsive means the game responds to user input like almost immediately. So, and that's very important increasingly. And besides this, there's another quality that we want in games like this, and that's determinism. So we'll be talking about that. So before we go further, like how we actually should think about games is like, what is a game really? Like so we have a function, okay? Like let's call it a game, like let's call it a simulation. So what does a simulation do? It takes the current state of the world, the player's input, and produces a new state. And this state is what we use to render the next frame, right? And you can think of almost everything in a game as some version of this. So like, let's take player movement as an example, or even weapons really. They're all really like just some or the other version of this. So you can think of any game really as, this function game making up like, I don't know, like hundreds of thousands of lines of just these little tiny things that take state, input, calculate the next state in a way. And we run this in a loop, right? And that's what essentially drives the game forward, like frame to frame, and you see things moving on the screen. So that's what it is really at the heart of it. So let's take a closer look at what a typical move function might look like, right? So we have a current position and the direction we want to move in, which is based on, okay, what keys are you pressing right now? So W might mean that I want to move forward, right? Or D means I want to move right. W plus D means I want to move forward and right. So we take the movement direction, increment the position by it, and we get a new position, right? And that's how it kind of goes. Now, if you want to move faster or slower, sure. So let's just scale the movement direction. And so now, by increasing the value of speed or lowering the value of speed, we're able to move faster or slower, right? But there's a small problem with this, and that's on faster computers we're going to be running this loop much more often. So what that means is that this position increment is going to happen more often. Which means that on different computers, our game will play differently, right? And I guess like almost everybody really knows what the solution to that is, right? And this is one of the first things that we all learn as game developers, is you scale the same calculation by just the time that's elapsed, right? And that's kind of it. But there's a couple of problems with that, and I'm going to get to it shortly. So let's take projectile motion as an example, okay? So projectile motion, an implementation of projectile motion would look something like this, right? So now only instead of incrementing position, we're also incrementing velocity, right? So velocity changes the same way as position, except the rate of change for velocity is now acceleration. So we multiply acceleration with delta time and we have a new velocity, and we use the same velocity to calculate a new position. And this is what we call semi-implicit Euler integration. And this is what a lot of physics engines actually use, right? And this is actually good enough for a lot of cases, right? But there's something here that all of us need to understand, okay? So one problem with this is that the output of our calculation kind of depends now on how delta time varies, okay? So the larger delta time is, right, like the faster we'll get to these values. But that's kind of okay. That's what we want in a way, right? We want to scale the calculation by time, right? That's what we did want. But this has some negative side effects on how this actually plays out. Like, so this is a plot of projectile motion, right? So the perfect white line is what the trajectory of this particular projectile should be, okay? But if we do the same calculation at different frame rates, these are the results we get, okay? And even worse, this white line is what you get if your delta time varies, which can happen on the same computer, okay? So there's a pretty simple trick to working around this or fixing this, and that's just use fixed time steps, okay? And that's what really all physics engines do, okay? And this brings us to networking, okay? So in like most modern networked action games, what happens is position of players and the state of the world changes very, very often, okay? Which is why the state of the world has to also be synchronized very often. So most of these modern multiplayer games, at least the multiplayer engine is written in a way where they use a tick-based system, which is pretty similar to the fixed update in a physics engine, okay? The other nice like side effect of using ticks instead of time is that we are using an integer value, which is like two computers cannot disagree on how that should translate to the delta time, okay? Because a floating point number, when we transmit over the wire, like we might have to compress the bits, and that value might mean something. Or if you actually use a timestamp, then that might need to be compressed. We can't really we can send the whole 4 bytes, but it might still if we end up compressing it, then the accuracy is going to vary. So in multiplayer games now, how you can start thinking about the same state from state and input is think of state at tick 100 as the game's state at tick 99 and the input at 99, and we get the new state, right? And this is kind of how a multiplayer game drives forward. And every time what a dedicated server will do is it will take like all of the changes in state at a particular tick and stamp them, with what tick they are, and send it to all the clients so that everybody is in sync and everybody is rendering the same world at the same tick. In fact, in the real world, the time, the actual like wall clock time that you see somebody move at might be different, okay? But the game's internal state is still being driven by this tick. So what that means is that like a tick 101 may have occurred at a different GMT time for me than somebody else, right? And that discrepancy will always be there, and there's not a lot we can do about that. So this way of, however, driving a game forward gives us a uniform frame of reference. So far we've kind of established that, okay, so if we want determinism, we should use fixed time steps, okay? So this is true in physics engines and in networked action games, right? And so we're probably thinking, okay, sure, so like if we can probably go ahead and start writing all of our gameplay in the fixed update, right? Right? But there are a couple of problems with that, and that is, so let's say that if we were doing our gameplay calculations 30 times a second, that's not going to appear great on displays that even run at 60 hertz, which this display is also basically 60 hertz, right? So it's almost like we are displaying the world at half the refresh rate of this monitor. And monitors that support like 120 to 144 hertz are becoming increasingly common. So this is kind of not a good thing because our customers care about this a lot. So one way to fix this is that we decouple our simulation and our rendering. So this is a typical Unity structure. Okay, we have fixed update, let's say, and we have our render loop. Oh, wait a second. Okay, I think Never mind. So this is actually like a bit more complex example. There should have been a simpler example here, but okay. So what's actually going on here is, so let's say we have a function, right? The projectile function. It's the same one that we saw a couple of slides ago, right? The same function. Right. So we have the same function. Now we're running it in fixed update at, let's say, 30 hertz. Okay. So our time.fixed delta time is going to be 1 by 30, right? So every 30 times a second, we're going to calculate a new position and velocity for this projectile. Okay. All we really do then is we um, override the render position with this new position. Okay. Here we would also override velocity as well, which let me see if I actually have an example of that. Okay, I do have an example of that. Sure. So if we override, we can now override the position that we should be rendering at. Okay. And in update, if we chose to directly use this value, then we would still see the hitching. Okay, that hitching is still not solved. So one way to solve for that is that we can smoothly interpolate between two previous values. Okay, so that's what's really going on here. So what we do is we first remember a previous simulated position. Okay, simulate a new position and remember that. And then in our update loop, in our render loop, we're basically slowly lerping from this value to this value. That's essentially what's going on over here. Okay. Though in the case of projectile motion, there's a pretty simple way to do this, which is really just repeat the simulation in render. But instead of now remembering just a render position, we also remember a velocity. And we use these values to simulate ahead. Okay, so this is actually not really using historical data. Okay, you can think of this as we ran a fixed update some time ago, and now let's say we are sometime into rendering after our last fixed update. And in that time, we've actually been calculating a render position, but we actually don't do any game logic here. Like we will not process things like did the projectile hit something. I mean, we could choose to do that. Like if we wanted to, let's say, show a decal somewhere that the bullet hit, or like the ball bounced, whatever, right? We could choose to show some effect here, but there would be no like game logic happening here. All game logic would be happening here. Here, we'd simply just take position and velocity and kind of render ahead in a way. So, oh, okay, same slide again. So let me show you an example of what this will look like when applied to player movement. So we have a capsule here representing the player. If I hit the WSAD keys, then the thing moves around. So this is what it looks like if we were simulating the game at 10 hertz, like 10 times a second, right? Which is not really that great, right? So now let's say if we were actually interpolating the position, then this is what we'd actually see, right? But the thing that's actually going on here is, if you notice the blue ghost, that's actually what my actual like simulated state is. So what's kind of happening is that rendering is catching up to what has been simulated. Okay. So when I actually hit a key, there's actually a delay. There's actually a delay of around 1/10 of a second before my character actually starts moving. Okay. Which some people are actually sensitive to. Okay. So this yet again is like it's okay, but not good enough for where we want to get to. Right. Cool. So I guess, I think I mixed up the slides here a bit. I'm so sorry. Okay. So in the case of projectiles, at least, there's another like nifty little trick that we can use to render ahead. Okay. Actually, before that, let me just show you what happens in the case of the player. So in the case of the player, so far we've been rendering has been catching up to what has been simulated, right? Let's say that we instead, what we do is we render ahead, like the same way how we're doing the projectile, right? Now what we're gonna do is we're gonna render ahead. In fixed update, we're gonna store our previous position and then use the same input and then just render ahead, right? So what is that gonna look like? Second, I think this broke, sorry. Okay, there we go. So now we're actually rendering ahead here. Okay, so what you'll notice happens is so our player is actually moving ahead of what's been simulated now. Okay, which is why the blue ghost shows up behind. So now we're not catching up. Like instead, what's happening is we're predicting where we'll be. Okay, but this introduces this error in our calculation, right? If you notice. So the reason this happens is because a fixed update hasn't actually picked up on the input that we're using to calculate render state. So what that means is that we've and because it run at different tick rates, like this is what ends up happening, which is what, if you remember, is what we noticed in the projectile motion, right? That if we sample the same simulation at different tick rates, then we get different results. And that's kind of what's going on here. Okay. And so at 10 hertz, this looks pretty bad. But if you were simulating the world at something more reasonable, like 25 or 30 hertz, it actually wouldn't look so bad. And this is kind of like a good enough solution to deal with the problem. And in the case of projectile motion, though, there's a very nice way for us to completely avoid this problem altogether by simply using the closed form solution for a projectile, which is you calculate new position using ut plus half at square. So this way, like our render and our simulation are never going to be out of sync. They're always going to be, they'll always have the exact and accurate result. So couple of things that we have to do in order to first deal with the error is we need to also change the way we handle input. Okay, so what happens is, so let's go back here. So let's say, so this is a fixed update, right, which is running at 30 hertz. So in order to do player movement, we'd have to use position here to calculate, player input here to calculate new position, right? But then what input value are we going to use? Do we use an input value that's arriving at 30 times a second? Though that's not the case, right? The thing is, in render, we probably will be using an input that's arriving at 60 or even 100 times a second. So that in itself is going to cause like this discrepancy, or there's going to be this error. So in a way, we kind of have to accumulate input that we receive in update, which is the 100 times a second, to be used in the one that we're running at 30 hertz. So you can kind of picture this as let's say if we were rendering at 60 hertz, then we'd get input twice, do rendering, and then we'll run a fixed update. Okay, do rendering twice, then do a fixed update, right? So we kind of need to gather up all the movement input here. Okay. Now you can probably just store that in a buffer. Okay, but a much more simpler way to do that is to just store whatever movement direction is multiplied by the time and keep also accumulating the time. Okay, and when it's time to actually use fixed update, the input in fixed update, we simply divide the accumulated movement direction by our accumulated time. This is kind of close to what you would actually end up doing in the calculation. So this is a neat way of, there's a neat replacement for, using having to use an array of inputs, right? Which might be as bad as like up to 4 or 8 if you were rendering way more often than if you were simulating. Right. So there's kind of a way that we can deal with that discrepancy in what we're rendering and what we're simulating. So what we'll have to do is we have to perform some error correction, because this error is bound to creep in, at least in the case of player input, right? Sorry, in the case of player movement. So one very simple way of dealing with this is that we slowly tend the render position towards whatever the real position is. Like we slowly just lerp it towards the actual simulated position, right? So let me just show you guys what that looks like. So what we're going to do now is, so you'll notice that there was this, let me show you the previous result just to be sure. So you can see that when I change direction, there's this bit of a snap, right? It doesn't actually like appear smooth as such. Okay, inputs, sorry, Unity is not really taking my input. So here you can notice that it's been now smoothed out. So this is using the same thing that I was just talking about, that we slowly move the rendered position towards where we actually should be. And what that really looks like is kind of like this. So if you remember the same pattern that we were using earlier of simulating the world, storing like a base, storing these base values that we have to now predict render on top of. But instead here, what we have is we actually have 3 sets of values. So you can think of like we have position and velocity, which is our actual like state of the world, okay? And then we have a reference render velocity and a reference render position. This is these are the positions and velocities that will slowly move towards, okay? And besides this, we actually have a render position and a render velocity, which is what we actually use for rendering, okay? And here we basically we just use the same function, just different inputs, okay? Which is, if you go back to the same thing that we've been talking about, where games are new state equals old state and input and time. So that's just all 3 of them here. But using different set of values here, and these values are being moved towards these values using these, which is just a simple vector 3.move towards. And so that's kind of the gist of it. So just to recap a bunch of things that we talked about. So you got to start thinking of games as simulations, okay? We need to start breaking up all the individual things that also happen in them as the simulations of state, input, time equals new state. And should be implementing games using fixed state if you want a determinism, but that means that your game's not going to be responsive anymore. So which is what we do is basically we render ahead, but having the ability to render ahead, it's really important that you start breaking up your game as in terms of new state equals simulate state and input and time. And in some cases only we have to correct if absolutely necessary. At least in the case of player movement we had to. In the case of projectile motion you won't have to. And there are quite a lot of like physical phenomenon that you might simulate in a game where you wouldn't have to do this, but some of them might require a different approach. But this way of thinking really remains the same. It's like, okay, how do I do the simulation and how do I render ahead? And what should my simulation function look like? And if you look at most of the examples here, they're almost always the same thing. Like our accelerate move is the simulation function that we're using here. It's just that it's using different inputs in different parts of the pipeline. And that's really the case with almost all of them. Like it's the case with projectile as well. We're using the same projectile function here. And yeah. So yeah, that's basically it.
I don't.
I do have a question.
All right.
Yeah. So in a game like Valorant, where you're simulating at 120 hertz, would you still end up doing some sort of correction because you're simulating at 120, you're rendering at 120? So then, would any sort of prediction or anything like that still?
If you're running on a display that can render faster than 128, yes, then yes.
Then you still have to.
We have monitors that go up to 240 hertz. So on monitors like that, you would have to do that. So it's not just about the monitor really; it's also about the computer. If the computer and the monitor can both display up to 240 hertz, then you have to. Like we have so rendering ahead is actually a trick really, but we have to give the player the illusion that they're moving immediately when they hit a key.
Right. Got it.
Yeah, questions?
Yeah, I have one.
So in case of prediction, can you talk a little bit about how does player-to-player collision or projectile-to-player collision would happen? Because you are predicting, right? So when whatever you are seeing on the screen, you expect things to collide in that state. So any high-level things like how does collision happen in a predicted state, or yeah.
So again, like going back to the same example I was showing. So if we simulate like at rates of like 30 or 60 hertz, if our server runs at that kind of tick rate, or a simulation also runs at that kind of tick rate, then we can probably do with not having to deal with what you're talking about. But I get what you're saying. That it's like, okay, like if I'm rendering more often, then I'll probably run into a wall, right? But then when the simulation actually runs, I'm gonna get pushed out. And yes, that's gonna happen. And error correction can probably deal with that to some degree, but that discrepancy will become lesser and lesser if your tick rate is higher. For lower tick rates, we kind of have to deal with it. If we don't want to deal with it, then the only other solution is that you do the exact same simulation again in rendering, which is so in a character controller, part of that simulation would be also performing collision logic. So you could deal with that as well. You could do it that way as well.
So similar question. So one is like player to player collision or player to environment collision. The other one is just hit detection. Like when you see somebody on the screen. So one is like when we talk about prediction, we are being predicted on our own game.
Yeah.
But the other players who we see, they are probably not. Let's say they're not predicted. They are just interpolated.
Yeah.
So if I see somebody, I shoot someone from a predicted state to an interpolated state. Like what are the ways of hit detection? Which there are multiple ways, but any way you can talk about, like, okay, I hit somebody who is in interpolated state, I'm in a predicted state. How would the hit detection work in a dedicated server environment?
Again, going back to that same example of just a second, let me find the slide. So if you remember, we were talking about how we remember state by tick, right? So here also, like, it's input by tick. So you kind of have a buffer, like the server can kind of maintain a buffer of previous state. This previous state doesn't have to be for the entire world. It can just be for players. And when we shoot somebody, there are a couple of things that matter here, right? At least like it's when did we shoot? So that's your like input at what tick. Like, so let's say in this case 99, right? But let's say I shot you at 87, right? So at 87, so I receive input for 87, and then fire input for 87, and then I can roll back the state to 87 and check. In a more advanced case, you could also do things like not store the state very often, right? Like only store like only every third or every fourth state, and then interpolate between them. That's one thing. That's another thing that you can do. Or even better, what you can do is you can keep all of the states and also like interpolate between them. Like if your input also has some sort of an alpha, right? Like if it's not on the sim, but it's between two sims. So that's what we call that's lag compensation basically.
All right, anyone else? Okay, well, everyone, that's it. We've got snacks in the back. Please help yourself, and thanks for coming, everybody. Thank you.